Welcome back to ECE 320A. We're in Unit 2 still. This is Video 6. Homework 2 is due. We're still reading through or completing our reading in Chapter 10, and exam number 1 is coming up at the end of Units 1 and 2, and you have some review material available to practice some previous exams. What I want to talk about today is this idea of or a generalization really of KVL and KCL when we have or when we're working with phasors. So when we're working with phasors, we have to keep track of the real parts and the imaginary parts, or really the magnitudes and angles. We have to keep track of all of those. We can't just be worrying about magnitudes. And we'll do that by looking at a quick KVL example to illustrate that in a series circuit, the generator voltage magnitude is not necessarily going to equal the magnitudes of the voltage drops across two of the reactive elements. And then we'll get into everyone's favorite, which is a word problem. And I know that you enjoy word problems from previous educational experiences. Think elementary, middle school, high school, math classes. Let's look at a word problem that illustrates how we can really start to play with or have fun with magnitudes and angles when we're dealing with voltages, complex power, etc. And how do we extract all of that into something that we can use to solve for what we need when we have a mix of given information in the form of a word problem. Let's now remind ourselves then that now that we're dealing with sinusoidal steady state environments, we have phasors. We have complex numbers for voltages and currents. And those complex numbers, what you should be seeing are directions and lengths. Lengths and directions, or hypotenuse for all of these things. Complex power, currents, and voltages. And because of that, we have to treat these voltages and currents vectorially. We need to add up voltages vectorially and currents. They have a direction and a length. So let's look at a quick example to try to illustrate what's going on. In this case, we still can apply Kirchhoff's voltage law and Kirchhoff's current law. It's just that we have to use phasors or vectors when we're doing the algebra or the manipulation with the numbers. In this case, for Kirchhoff's voltage law, we can apply that to this series circuit, and I hope it's clear that if we start down here in the lower left, we can now move around that circuit and sum up the voltages around that network to find that we have now minus V sub G as a phasor plus V1 as defined plus V sub 2. We're entering their positive terminals as we've defined them, and we're then back to where we started in the lower left-hand corner. So that now we have this combination of vectors that sum to 0. It's not just a number, it's now a length and an angle for all three of these that produce some kind of end result, which in this case has to satisfy Kirchhoff's voltage law, which says that the vector sum of those has to equal 0. Or we could write it another way. We could say that then V sub G, if we add V sub G to both sides, we'll see that V sub G is now the sum of V1 plus V sub 2. And just to illustrate that, we could say, well, suppose that V1 goes here as a vector. So now V1 and all of these vectors, remember, their angles are defined with this horizontal real line or horizontal line going off to the right. So V1 has a length and an angle. And let's say that V sub 2, let me see if I can do this in different colors. Let's say V sub 2 now has an angle. Again, it's added on to the head of this vector for V1, and let's say that this V sub 2 phasor has an angle theta sub 2 and a length, the length of that vector V sub 2 bar. And it's really saying that V sub G is the vector sum of those, so that V sub G ends up going to that head of V sub 2. And I hope it's clear that if you now added up the length of V1 and the length of V sub 2, since these three vectors really are forming a triangle, I hope it's clear that you can see that the length of this third side is actually not enough to give you the length of the other two sides. So if you flattened V1 and V2 or align those along V sub G, you would see that they get bigger. Their sum gets bigger than V sub G, and that then says that we can't just treat these voltages or currents for that matter as numbers. We have to treat them as vectors. So let's apply this to the following word problem. We're going to keep, or we're going to preserve, this series network configuration. We have a generator. It's supplying two loads, two impedances, Z sub 1 and Z sub 2. That's really the structure that we're working with. And now we have the following worded description of how all of these quantities are connected or interrelated. So first, we're told, let's assume or suppose that the voltage magnitude across Z sub 2 is 40 volts. And we're also told, so let's maybe even write that down as we're going. So now we know that the magnitude of V sub 2 is 40 volts. We know that Z sub 2 is absorbing 80 watts. So P sub 2 is 80 watts, and Z sub 2 is inductive. Well, we know that we have a Q sub 2 if it's an inductive load. Maybe we don't know what it is, but we do know that it's positive. So that's one of the pieces in a sentence that we're told, something about load number 2 or impedance number 2. It has a real power of 80 watts, it has a magnitude of 40, and it is an inductive reactive power. Suppose that the supply, the source, is now 120 volts in terms of its magnitude. So now we have a magnitude of 120, and the real power supplied by the source is 100 watts. So now we know that the source, and I may label that subscript S, subscript G, but we now know that it has 100 watts, and the total load is inductive. Okay, well, so Z1 and Z2 in combination are going to be inductive, but that does not necessarily mean that Z1 is inductive. Maybe Z sub 2 has more inductance than Z1 has, or maybe Z1 is capacitive and it doesn't overweight the inductive portion of Z sub 2. Oh boy, we have even more. So now we're told suppose the series current has an RMS value of 5 amps, and assume the current phase is used as the reference phase, and it's 0. So now we're told something about this I. We now know that I is 5 at 0 degrees, so now we know that we don't know this angle. We'll have to figure out what that is. So let's now say that the source angle is some unknown quantity, theta sub G. So hopefully now we have that information floating around, and we have to make sense of that. And what can we start to say? Well, let's just start seeing what we can about this particular circuit. So we have sinusoidal steady state information, or it's a sinusoidal steady state problem. And let's just summarize what we've been given. And maybe it will start to make sense what we have. Load number 2, we were told that the magnitude of its voltage, RMS, was 40 volts. We had a real power of 80 watts, and Z sub 2 was inductive. All right, we also were told something about the source. I'm trying to buy myself time. I'm guessing I'm in an interview and now somebody's wanting me to solve this problem, and I'm trying to figure out how do I do this? So I'm buying time. The source voltage magnitude in RMS was 120 volts, and the real power supplied by the source was 100 watts. We were also told that this total load was inductive. So far, we don't know what Z1 or Z2 are. We did know, or we were given, the magnitude of our current, and that current is going through every one of those elements. The source, the generator, and each of the loads, Z1 and Z2, are experiencing the same current since it's a series circuit, and maybe that's going to help us. So now we know the magnitude of the current going through all 3 of those devices. And what we're wanting to do, did I make that clear? We want to actually find the phasor voltage for load number 1. Maybe I didn't say that before, but it's here now in black. We want to now find V1. We're given the magnitude of VG. We're given the magnitude of V2, and we know we can't just play with the magnitudes based on what we just did with this quick example before. So we know that we can't just add magnitudes and end up with what we want. We actually have to try to find angular information and deal with V1, V2, and V sub G vectorially. So now what do? We want to find, let me just remind myself since I kind of forgot that before, we want to find the phasor value of Z1's voltage. So now we were also told that I sub S was the reference phasor. Remember, I'm trying to buy myself time. I'm in an interview and I'm trying to think on the fly what's going on. So now I can actually write the phasor form of I sub S. I know its magnitude and I know its angle. And that was given as an RMS quantity. I can also remind myself that I have a series circuit and KVL still works in that case. I now know that minus V sub G plus V1 plus V sub 2 is equal to 0. Or I now know that V sub 1 is V sub G vectorially minus V sub 2. As phasors then, or as vectors, V1 is equal to V sub G minus V sub 2. So if I could find the angles of V sub G and V sub 2, I'd be in business. I could then compute, because I could now add these up component-wise or vector-wise to find the phasor value of V sub 1. All right, now I need to go back and figure out what I have. I have the magnitude of V sub 2, and I have the magnitude of the current, and I have this particular connection. But now what does magnitude of voltage and magnitude of current, those give me actually apparent power, don't they? And I have the real power of V sub 2 or of load 2. So now I have a little bit better understanding maybe of what I have. I have the real power and I have the apparent power. And oh, if I remember my formula for real power, that actually gives me the power factor of load number 2. And once I have the power factor is related to the voltage and the current angles. And I already know the current angle. So that's going to allow me to obtain the angle of my voltage for load number 2. So let me write that down. I now have in my possession the magnitude of V sub 2's voltage, or the voltage V sub 2, and I also have the current through load 2, which is the current through everything, and I have the magnitude of that. So that says that I now have the apparent power at load 2. So now I just start reminding myself of what I have. I know that the complex power of load 2 satisfies V2 as a phasor times I sub 2 complex conjugate. And this I sub 2 is the same as I sub s since it's in series. Well, if I know that this is true, I could take the magnitude of both sides, and that's still going to be true. So I know that then the magnitude of S sub 2 is the magnitude of V sub 2 I sub S conjugate, which is now the magnitude of V sub 2 I sub S. So this is now justifying what I said before, that I actually have the apparent power of load 2. And what I'm wanting to do now is start thinking in terms of triangles. If I have the apparent power and I have the real power, I have the hypotenuse and I have the horizontal. Oh, that allows me now to find the angle between them. So P sub 2, well, just in general, remember what our real power formula looks like? That's now the apparent power times the cosine of theta, where the cosine of theta is just the power factor. That's in general. So for us, we can apply that to load 2 and say P sub 2 is the magnitude of the complex power for load 2 times the power factor of load 2. And if that doesn't help any, remember what we have. We know this, and we know this, which means that we can find what this angle is because we know we are dealing with a right triangle. We maybe don't know what Q is, but we can find that also if we now know the hypotenuse and one of the sides. And so from this, let's go ahead and figure out what we have. We can find then that the power factor of load number 2 is P2 over the apparent power of load 2. We were told this was 80, and we had a voltage of 40 amplitude and a current amplitude of 5. So that now we have, well, if we just start simplifying this a little bit, 40 goes into 80 2 times. So now we have 2/5, or power factor of load 2 is now 4/10. So with power factor 2 equaling the cosine of theta sub 2, and we know that it was inductive, so that we know that the current is lagging the voltage. That gives us the sine of theta sub 2, which is why I could draw Q showing positive up above. Now we know that theta sub 2 is plus the inverse cosine of 0.4. Or that's now 66.4 degrees in the positive direction. And since we know that the current was the reference phasor, then V sub 2 is actually going to be 40 at 66.4 degrees. And the reason I can say that is because theta sub 2, which is this, really that's the angle of load number 2's impedance, that's now equal to theta V sub 2 minus theta I sub 2, and that's now 66.4 degrees minus 0 degrees, or we really knew what theta sub 2 was, and that allows us then to conclude that theta V sub 2 is actually 66.4 degrees. So now we have V sub 2. Where are we? Well, we want to use this formula. V1 is equal to V sub G minus V sub 2. And now we actually have V sub 2. We now need to find the angle associated with our source. And then we're good to go. So now let's look at the source power. Well, again, maybe we're buying time, so we say, okay, the formula, the complex power formula for the source is going to be the voltage of the source, phasor, times the conjugate of the current phasor of that source. And we know that. But if we write this out, maybe we're there's what we have. And we actually know what I sub s conjugate is. But let's keep going. Let's keep writing this out. So now we have V sub s, I sub s, the magnitudes of those, at an angle of theta sub V sub s minus theta sub I sub s. So there's our polar form of the complex power of our source, written in terms of the magnitude and an angle. But that phasor can be written not in polar form, which is what we now have, but in rectangular form by expanding that phasor into its component parts. Its real part, which is associated with the cosine, and its imaginary or orthogonal part, which is associated with the sine. Or we now know that V sub s, I sub s, is now cosine of theta V sub s minus theta I sub s plus j sine theta V sub s minus theta I sub s. Or, pushing that magnitude through both pieces, we now have V sub s, I sub s, cosine theta V sub s minus theta I sub s, plus j times V sub s, I sub s, sine theta V sub s minus theta I sub s. Or this is now P sub s plus j Q sub s. Did anyone hear me say I'm buying time? So now I'm buying time, but we were given some of this information. We were actually told the power, the real power of our source. It was 100. So now we know P sub S is 100 watts. We also know the magnitude of our generator or our supply. That was 120. And we know what the magnitude of I sub S was. We even know the angle of our current. That was 0. It was the reference phasor. So right now we know, and this is P sub S, and this is Q sub S. And what have we found? We know P sub S, we know V sub S, we know I sub S. Now we can find the power factor of our source. We can find cosine of theta V sub S minus theta sub I sub S. See how this works? We're buying time, and that time that we just bought has helped us. We now know that P sub S is the magnitude of V sub S, magnitude of I sub S, cosine theta V sub S minus theta I sub S. And this is the power factor of the source. So that now we can say the cosine of theta V sub S minus theta I sub S. And we know that this guy is 0 degrees because it was the reference phasor. That's now equal to P sub S over V sub S I sub S. P sub S was 100, V sub S was 120, and I sub S was 5. And I can actually divide 5 into 100. That gives me 20. So now I know that this cosine of the effective impedance seen by the source is 20 over 120, or 1/6. So that now I can find theta V sub S, since theta I sub S is 0, theta V sub S is the inverse cosine of 1/6, which is 80.4 degrees. And now hopefully you can see that I am getting somewhere. Now I can start playing with the voltages as phasors, since I've actually extracted the information that I need. I now have the source voltage phasor is V1 plus V sub 2 phasor-wise, so that V1 is now V sub S minus V sub 2. And V sub 1 now is V sub S, well, is the magnitude of V1 at an angle of theta V1, but that's now V sub 1, I'm sorry, V sub S times cosine of its angle, which was 80.4, plus J V sub S magnitude sine of 80.4 degrees. This piece, or these two pieces, are V sub S written in rectangular form, and since I'm trying to subtract angles, I need to sort of convert them into rectangular form to show it in your calculator. You could probably just subtract these polar forms and it would be fine. But now I need to take away from that V sub 2, which had an amplitude of 40 and an angle of 66 degrees. So there's the real part of V sub 2, and here's the imaginary part. Again, this is now V sub 2, just not written in polar form, but written in rectangular form. If I do the algebra, I end up with V1 equaling 4 plus J 81.7 degrees, which is now 81.8 at a big angle, almost 90 degrees, 87.2. And this is now the magnitude of V1 at an angle of theta V1 degrees. And I hope then that you can see, and that's what we were trying to find. We were trying to find V1 as a vector, as a phasor. We now know it has an amplitude of 81.8 and an angle of 87.2. And that we extracted from that word problem description. And one thing that you can take away is that hopefully it's clear that the magnitude of V1, which is 81.8, is not quite equal to the magnitude of V sub s minus the magnitude of V sub 2. But since these angles are big, it's not too bad in terms of approximation. But here we had 120 for the magnitude of V sub s, we had 40 for the magnitude of V sub 2, and we have then 80 for the result. So it's almost, but it's in fact not the same. We can't just add and subtract magnitudes of voltages or currents. In this case, we had V1 going up here at an angle of 81.8, which that's not quite 81.8. There's V1. Then we had V2 going off here, and that then produced V sub s, and this angle was not quite 81 point, or no, wait a minute, what did I have? This was 87. I'm getting my angles and magnitudes confused. This actually had an angle of 87 degrees. This length was 81.8. This length was 40, and it had an angle of 66 degrees. And V sub s had an angle of 80.4 degrees. Again, those two or those three lines don't add up. They add up only if you consider them as vectors. And likewise, you need to make sure that when you're dealing with not only voltages, currents, those are also phasors, and you have to make sure that you're treating those vectorially as well. Meaning if you now had somebody giving you a current supply feeding two parallel impedances, then I1 and I sub 2 will solve or satisfy or obey Kirchhoff's current law, which says that I sub s as a phasor is equal to I sub 1 plus I sub 2. But you can't just add their magnitudes. As an example, if we said that I sub s was 10, I sub 1 could be 7.13 at an angle of minus 52.48 degrees, and I sub 2 could be 8 at an angle of 45 degrees. And hopefully that's clear that 15, or almost 15, is definitely not 10. So you have to treat currents and voltages when we're dealing with sinusoidal steady state as phasors. We have to treat them vectorially which means we have to use magnitudes and angles in the correct algebraic way in order to come up with the correct answers.